we're now going to state and prove the main theorem for bounded generators of Markov processes. Let Qt be a Markov transition semigroup over any state space, and suppose that we have this strong continuity property. As a function of t, Qt is operator norm continuous at 0. We'll explore a little later exactly what that means in contexts where this kind of continuity really makes sense, the discrete setting. If that holds true, then in fact, Qt is continuous for all non-negative time in operator norm. The generator exists, that is, the right derivative of Qt at 0 is defined and is in fact a bounded operator, and that bounded operator generates the semigroup. The semigroup is given by e to the ta, which converges uniformly in T in operator norm. In particular, Qt satisfies the Kolmogorov forward and backward equations right here, for which in this nice bounded A setting, the unique solution is given by this exponential power series. Now, before we delve into the fairly delicate proof, let's look at an example that we already actually went through several lectures ago, but that we can now justify every step of rigorously using this theorem. Remember the Poisson process. That's a continuous, homogeneous time Markov process on the discrete state space, the natural numbers. Its transition kernel function was given like this, as we calculated, if we have intensity, the transition rates, given by lambda. Now, in this case, the transition operators are given by these matrices, and therefore, to check operator norm continuity of the transition operators, we can, as we showed in the last lecture, compute that in terms of the infinity norm of these matrices. That is, the maximum row sum, the supremum over all I of the sum over j of this quantity here. Well, let's break that sum up. Well, first, this is a sum over all j here. However, for each fixed I, all of these terms here are 0 if j is less than I. So this sum really starts at I, and it's going to behoove us to break it up into the case j equals I and j greater than I. If j is equal to I, then this delta ij term is included. That gives us e to the minus lambda t times all of this stuff is just 1, minus 1. And if j is bigger than I, well, then we just get e to the minus lambda t times lambda t to the j minus I divided by j minus I factorial. Now, we can re-index this sum. Instead of indexed by all j's greater than I, let's index it by this term, j minus I. And that's going to reduce to the sum, let's call it k, equal 1 up to infinity of e to the minus lambda t to the k over k factorial. Well, this sum is just the exponential power series with the first term missing. And that's going to give us e to the lambda t minus 1, but we have that overall factor of e to the minus lambda t there. And that gives us altogether 1 minus e to the minus lambda t. But that's exactly what this is, because this is always less than or equal to 1, since t is non-negative and lambda is a positive constant. So what we get is that this is equal to 2 times 1 minus e to the minus lambda t. And that indeed does go to 0 as t goes down to 0. And so we see that the transition operators for a Poisson process are operator norm continuous at 0. And thus, from these calculations, we do find a bounded generator. Now, we explicitly computed the generator, which is a finite difference operator, in lecture 39.2. We can view that example as a sanity check for this theorem, since it is easy to compute in that case that that finite difference operator is a bounded operator. So let's prove this theorem. To start, we need to see that Qt is itself bounded, but in fact, we already showed that in previous lecture 39.1. The operator norm is less than or equal to 1 because we showed that Qt f supremum is always less than or equal to the supremum of f. But in fact, it's equal to 1 because we also know that Qt of 1 is equal to 1. And therefore, the ratio of the norm to the norm here can't be anything less than 1 in Suprema. Now, our assumption in this theorem is that Qt is operator norm continuous at 0. To begin, let's show that it's actually operator continuous everywhere. And to do that, we're just going to use the semigroup property. For any non-negative t, let's move away from t by a small amount h. To begin, let's move forward in h, so take h positive, and look at the difference, qt plus h minus qt. We'll measure that in operator norm. Well, qt plus h by the Chapman-Kolmogorov equations is the same thing as qh composed with qt. And now I can factor out the qt there. And use the submultiplicativity of the operator norm. Now this is just constantly equal to 1, so that's not going to bother us. And our assumption is that this tends to 0 as h goes to 0. So that shows us right continuity of qt as a function of t. Similarly, we want to show that if we approach t from the left, we get continuity. So in this case, let's look at q at t minus h minus qt. This is only going to make sense if we take t bigger than h, of course, but our goal is to do this for h getting arbitrarily small, so that should be no problem if t is positive. In this case, we're going to use the Chapman-Kolmogorov equations to factor out a qt minus h from the second term. And we'll do the same calculation, factoring out the qt minus h, and using the submultiplicativity of the norm, this is going to be less than or equal to I minus qh, operator norm, times the operator norm of qt minus h, which is just 1. And so, again, by the assumption of the theorem, that goes to 0 as h goes down to 0. Great. So that shows us that operator norm continuity at 0 gives us operator norm continuity everywhere. Now we can do a similar calculation to approach the derivative. Let's look at the finite difference quotient that defines the derivative, qt plus h minus qt over h. We can use the Chapman-Kolmogorov equations just like we did above and factor out the qt from both of those. Let's say on the right, getting qh minus the identity divided by h times qt, or we could equivalently factor out the qt on the left from both. That's why we're going to have two-sided Kolmogorov equations here. So what that shows us, working for now with factoring out on the left, that if t is non-negative, and if b is any bounded operator, if I take the difference between this difference quotient and qt times b, using this expression here, that's equal to the norm of qt times qh minus the identity over h minus b, all measured in operator norm. And if we want, we could have put the qt on the other side of both of these, and then we would have been able to write it on the right. And again, using submultiplicativity and the fact that qt has norm 1, that is less than or equal to just the operator norm of qh minus the identity over h minus b. So what that shows us, taking into account the fact that we're working with positive h here, is that qt is right differentiable at t, which is exactly to say that the operator norm of this limit exists. That happens if and only if this limit exists, which is to say that the right derivative at 0 exists. That's what we defined to be a. And moreover, that happens if and only if, putting a equal to b in these equations, that qt a, or a qt, is the result that we get from this derivative. And left differentiability is going to work much the same way, just factoring out a qt minus h like we did in the calculation here. So what all of that shows us is that the differentiability that we crave everywhere and the forward and backward Kolmogorov equations are going to hold so long as we can show that this limit exists. Okay? It all hinges on showing that this right derivative of the process at 0 exists. But we can turn that around. In order to show everything we want to show, which means in order to show that this right derivative exists, by this calculation here, by this if and only if, it suffices to show that Qt is differentiable at some point, any point. Because if the limit here failed to exist at some point, this calculation would show that this limit would fail to exist. So in order to show that this one exists, it suffices to show that the process is right differentiable at any given point that we'd like to choose. This should remind you of our calculations in order to show that the only memoryless distribution is the exponential distribution, where we showed, via similar calculations, that differentiability at all points was equivalent to differentiability at 0, and therefore differentiability at any point. That's what the semigroup property does for us. Now, we're going to show this differentiability at any arbitrary point, and we're going to do it with a nice trick due to Swedish mathematician Lars Gording. Gording's trick is the following. We're going to use the fundamental theorem of calculus in a clever way. Fix any epsilon greater than 0, and consider the following operator on the space of bounded measurable functions. It's a normalized integral of qs with respect to s. To be clear, what we're saying here is that b epsilon is the operator which, when acting on a function f, gives us the new function which we get by applying qs to f. That gives me a bounded function for each s, and then we integrate that function with respect to s over the interval from 0 up to epsilon, renormalizing by the length of that interval. This makes perfect sense because, if you like, we can evaluate this at any state x. And this, as a function of s for each fixed x, is a really nice function, considering the fact that qs is operator norm continuous in s. So this will certainly be a continuous function of s for each x, and therefore this is really just a Riemann integral. But we can leverage the semigroup property to show, with the change of variables formula for Riemann integrals, a really nice regularity property here. If I apply this operator b epsilon to a function which is in the range of qt, so that is, if I take b epsilon times qt applied to f, well, that's just by definition this here. I'm putting qtf in the definition of the operator of b epsilon. And now I use the semigroup property because qs times qt is qs plus t. Well, by definition, what that means is that the operator b epsilon qt is this integral here. But now we can use the change of variables formula and the translation invariance of Lebesgue measure, which is what we're integrating against here, to write this as 1 over epsilon times the integral from t up to t plus epsilon of qu du. Now here's the thing. Inside here we have a uniformly continuous function on any compact interval, and this is an integral of that continuous function over a compact interval where the domain that you're integrating over depends on t in this nice way. We have a nice theorem that handles integrals like that. It's called the fundamental theorem of calculus. And what it tells us is that, therefore, this function of t is continuously differentiable. And its derivative is given by evaluating that function at the endpoints. Great. Now, what were we trying to show here? We wanted to show that qt is differentiable. And what we've shown is that b epsilon times qt is differentiable. Surely that means that qt should be differentiable as well, right? Because b epsilon doesn't depend on t. If I multiply a function by a constant and find that it's differentiable, that function must have been differentiable. Except, in order for that theorem to make sense, the constant had to be non-zero. I could take a horribly non-differentiable function, multiply it by 0, and get a differentiable function. Now, in the reals or complexes, being non-zero is the same thing as being invertible, but for operators, that's not true. Here's the catch. In order to recover differentiability of Qt from this, we need to know that B epsilon is an invertible operator. Well, it turns out that it is, at least for sufficiently small epsilon, and that's where Gording's argument comes in. In order to see that, we're going to basically explicitly compute its inverse, at least as a power series. To make the notation easier, let's let T be 1 minus B, and we're going to define this putative inverse, I'm going to call it C, to be this geometric series, the sum of T to the n ranging over all natural numbers, provided that that sum even makes sense. Well, we'll see in a moment that in fact that series converges for all small epsilon, but let's for the moment assume that we know that it converges. If so, C epsilon actually defines the inverse of B epsilon, at least a left inverse, which is what we need here. Why is that? Because what is this sum? It's just the limit. It's going to be a limit in operator norm of the partial sums up to a capital N. And so if I multiply that limit by B on the right, I can move that B inside the limit. And the reason I can do that is that B is a bounded operator. It is a Lipschitz continuous operator in terms of operator norm, and so I can pass it through operator norm limits. Now B is 1 minus T, and so this is T to the N times 1 minus T, which is T to the N minus T to the N plus 1 inside that sum. But that is a classic telescoping series. Starting at little n equals 0, this is 1 minus t plus t minus t squared plus t squared minus t cubed all the way down the line. So what we get is that that whole thing just adds up to this. So this is the limit of this quantity here, and that limit is just going to be 1 minus 0. It's just going to be the identity operator. The reason is that this must go to 0, and that must go to 0 because it's a tail term in this series, which we're assuming converges, which means that the terms must go to 0. Now, I said that this gives us a left inverse, but you can easily check that we also have that B times C is the identity matrix by the same argument. So all of this relies on this series converging in operator norm. Why does it, or when does it? Well, again, using the Weierstrass M-test, it's going to converge when the operator norm of t is strictly less than 1. The reason for that is by the submultiplicativity of the norm, the sum of the norms of the terms that we're trying to add up is going to be less than or equal to that operator norm to the nth power summed up. And in this case, that's going to be finite because this sum will equal 1 over 1 minus the operator norm, which is going to be finite. So by the Weierstrass M-test, again leveraging the completeness of the space of bounded operators in the operator norm, we will find that indeed this series converges, defining this operator here, which is the inverse of B, provided that this t, 1 minus b, has operator norm strictly less than 1. So that's the clincher here. We need to see that the b that we defined, when subtracted from the identity, has small operator norm, less than 1. Well, let's just look at its definition again. The operator norm of this thing is the supremum over all supremum 1 functions of I f hat minus b epsilon of f hat, supremum norm. Now the definition of b epsilon is given right here, and now we're going to do a trick that we've seen before, which is to put this f hat inside the integral as well. Here we're applying qs to f hat and then integrating, but if I don't apply qs, I just have a constant with respect to s here. And so I can write this as 1 over epsilon times the integral from 0 up to epsilon of f hat ds. That might seem silly, but it means that we can combine things as 1 over epsilon, the integral from 0 up to epsilon of f hat minus qs f hat ds. Now we can use the triangle inequality for this Riemann integral. But this quantity inside here, which is identity minus QS applied to f hat, its norm is, by definition of operator norm, less than or equal to the norm of I minus QS, because f hat has norm 1. So that shows us that this, the operator norm of I minus b, is less than or equal to the normalized integral of the operator norm of I minus QS. Now again, this is a continuous function of S, so this is just a Riemann integral. And Riemann integrals satisfy the mean value theorem for integrals, which says that that normalized integral is going to equal the value of the function at some point, call it S star. In between the two endpoints of integration. But hey, our assumption throughout this problem is that qt is a continuous function of t in operator norm at 0, which is to say that as S star goes to 0, this goes to 0. And since we're taking epsilon as small as we like here, as epsilon goes to 0, S star goes to 0, and that means that this goes to 0 as epsilon goes to 0. Therefore, we can choose sufficiently small epsilon so that this quantity, which we now know goes to 0 as epsilon goes to 0, is less than 1 for all sufficiently small epsilon. That means that for all those small epsilons, this geometric series defines an inverse to b epsilon, which says that if we write down the difference quotient that's going to define the derivative under limit for us, and just multiply it by c times b, which is the identity operator, that gives us this quantity here. Now if we take the limit as h goes to 0 of both sides, we can use the fact that c is a bounded operator, which means it passes through operator norm limits, and pull it outside, and that gives us c times the derivative of b epsilon times qt. That's what we showed using Gording's trick is a differentiable function. So this derivative exists, but this argument shows us that this on the left-hand side, which is equal to the derivative at time t of qt, can be recovered from this derivative, and therefore this is differentiable. So we've shown that qt is actually differentiable at all points. In particular, it's right differentiable at 0, which is to say that our generator exists, and in fact it is an operator norm limit of bounded operators, which means that it's a bounded operator. Concluding the proof. So let's just summarize one more time. Under this strong continuity assumption that the semigroup is operator norm continuous at 0, we get that it's actually operator norm continuous on the positive real line. The generator exists and is a bounded operator, and the semigroup is operator norm differentiable on the positive real line and satisfies the Kolmogorov forward and backward equations. And as I said before, it's now an easy matter to check that this uniformly convergent power series defining the exponential is indeed the unique solution of this ODE, which makes sense in this context precisely because our generator A is a bounded operator. Now, the sad fact is that in most interesting cases, this assumption is just too strong. The generator will not be a bounded operator. But there is one important setting where this kind of continuity does make sense, and we'll use it to get a firm understanding of continuous time Markov chains on countable discrete state spaces.